Good day, everyone. Welcome to ME 174.1 lecture on airfoil performance simulation. Now, we're doing this because there is a super typhoon currently running the gauntlet upwards of Luzon. I believe that Metro Manila and Cavite are on orange alert as of recording. So if you're currently staying there or in the northern parts of Luzon, please stay safe as much as possible. So this lecture is will not lead into the experiment for immediately. You might not be at least ready or at least prepared for that. I want to have you be in person, run some initial airfoil tests before we go deep into this. So I believe I'll just be setting up a short quiz for this that will have a very long deadline to ensure that most of you will be, at least partially, will have most of your focus, or at least more of your focus on safety wherever you are. So, all right, let's begin. Now, when it comes to airfoils, there is quite a lot of new terminologies. And if we start off this discussion without talking about those, you might get confused about what we're talking about. So let's begin here. Now, when it comes to airfoils, there is a lot. There is a lot of new terms to talk about, but most of them are rooted in this particular uh, geometry. So when we usually talk about airfoils, most of everything that we know, or at least everything here on this graph, will be defined relative to what we call the chord line. So the chord line is the shortest distance from what we call the leading edge, the front of the airfoil, to the trailing edge, which is the back end of your airfoil. When we measure the angle of attack of an airfoil, we usually look at the wind direction relative to the chord line. So that is why chord line is important. Most of these terms can be specified in terms of percent chord line. So if you want to examine different kinds of airfoils, eh, you want to ignore the effect of scale, you can just specify, oh, the this value is this percent of the chord, or this value is zero point zero 0.05 of the chord, etc. Now, for the upper and lower surfaces, there are no specific terminologies. It is what it is. Uh, Now, when it comes to airfoils, not all of them are asymmetric, just like this. However, it is quite common to have a upper surface that is more curved than the lower surface, or at least it gives you this kind of beluga whale shape, which is most common and more common nowadays. Now, if you take a particular point on the upper surface and then you trace a line down to a point in the lower surface and you get the midpoint, and you do that for every single slice of the airfoil, you get what we call the camber line. Now, the camber line is kind of the indication of how eccentric or how asymmetrical your airfoil really is. And at some point along this camber line is the maximum camber. So this maximum camber is usually measured from the chord line as well. So if you want to say maximum camber, you usually say, uh, okay, I want 4% from the chord line. So you can have a airfoil that has a maximum camber 4% of the chord length. So this times zero point zero 0.04, that is the maximum camber. Now, airfoils can also have their maximum thicknesses as well. Sometimes this maximum thickness will occur at the same place as the camber, sometimes not. It really depends, and there is no unified way of defining maximum thickness, essentially, especially for other airfoil families, aside from what we explored. Now, let's talk about how the airfoil generates lift. Now, when I was a kid up to undergraduate school, I had a lot of confusion as to how the airfoil actually does, or how the airfoil generates lift, because I keep getting one fact and then this other person or this other academic refutes that. But I never delved deep into which one is actually true, which one is not. Now, if you turn your attention to this animation, it actually shows you how fluid flows over the airfoil. And what you see here is that when the fluid meets the airfoil, it splits into two different flows. The flow at the upper section appears to move a lot faster than the section at the lower surface. So, in effect, what this means is that since the fluid is at the upper surface is moving faster, you get a much lower pressure than at the bottom. So this pressure difference is actually what causes lift. Now, why does the flow accelerate at the upper surface? That I think it's because the upper surface meets the airfoil at a very no, scratch that. I believe at the upper surface the flow is forced to divert upwards at a more extreme turn. While you think that the flow would actually slow down, what happens, I believe, is that there is a loss of pressure energy because it is forced to divert. And when it's forced to divert, there's kind of this nozzle type of effect wherein you pinch the area where the fluid is flowing so then it moves faster. And because it moves faster, if you recall from NSI 14 or NSI 16, a faster moving fluid has a lot less pressure behind it. Hence, you get this pressure differential. Now, this pressure distribution, if at least done in proper conditions, it should result in a net upward force on the airfoil. So this is how we get lift. Now, this is an important term here. You might see. Oh, sorry, my mouse was. So this is an important distinction. The lift force is not a pushing force. No? It doesn't push you from the bottom. It actually sucks you upward. You'll get that sensation when you're flying a very small aircraft, small fixed wing aircraft. And that if you just move a little fast, uh, you tend to get sucked up. You don't feel something pushing you up. Rather, there is kind of a suction force pulling you upwards. Now, for this pressure distribution, if you calculate the net effect in a particular direction, before we go that, I forgot to discuss. We can actually normalize this pressure distribution, just like all things in fluid dynamics, such that we get the pressure coefficient. So the pressure coefficient is kind of the pressure at that particular point normalized to the free stream pressure. So that's it. Now, if we take this pressure distribution, which is described by our pressure coefficient, and we get the net components in a particular direction, we can get the forces. Now, for those components, if we get the net vertical effect of that pressure distribution, we can get the lift force. Now, the lift force also has a dimensionless equivalent, as with all things in fluid dynamics. And we call it the lift coefficient, or C sub L. So the C sub L quantity is just the lift force over the free stream force that's being exerted by the fluid around it. So let's break down the variables used. So L is the lift force, rho is the free stream density, U here is the free stream velocity, and S is the top view area. Or in some aircraft circles, this is called the planform area. So the planform area is the area of the wing from the top. Now, if you take the net horizontal effect of the pressure distribution plus the skin friction, you actually get the drag force. So as I mentioned, the drag force consists of two parts. You have friction drag from the shear or the boundary layer, and you have pressure drag that is developed from the pressure distribution. And you also have what we call the drag coefficient. So this is just a drag force over the free stream force developed on the uh, by the fluid on the air. So a lot of normalization and ratioing. This part for the course for fluid dynamics. I think it's about time to get used to that. Now, all right. So let's look at our pressure distribution. Now, if you change the angle of the airfoil with respect to the fluid direction, you will get a different pressure distribution. If you get a different pressure distribution, you will get differing lift and drag values from what you had before. And if you plot that with respect to the angle of attack, you get this particular set of curves. Now, the x-axis is, of course, the angle of attack, but the vertical axis depends on the curve. Now, here, blue indicates lift, the lift coefficient, and red here is the drag coefficient. Now, what you notice here is that as the airfoil angles upward, the lift increases, but only up to a certain point. And it starts to decrease after you exceed that particular angle. Well, for the drag, it starts out small, but it just grows and grows as you increase the angle of attack. Now, alright, so why does lift not engage, or why does lift not behave in a similar way to drag? That is because lift is generated mostly through contact of the fluid over the airfoil. So when the fluid separates from the surface, that surface no longer experiences any of that suction pressure that you would otherwise see when the fluid is attached. And if enough of the surface becomes disengaged from the fluid flow, eventually gravity might win over the lift force. And this is when we get what we call the stall situation. If you've watched some aircraft accident documentaries or even short videos, you might see some incidents that involve stall. So stall is a very dangerous situation for fixed wing aircraft because the moment you hit stall, there is essentially no lift generated. Or at least there is not enough lift to counteract the force of gravity. You will have a very dangerous situation depending on how high you are above the ground. Now, this situation that you typically want to avoid, that is why there is a lot of testing involved in the type of airfoil that you're using for aircraft. Now, if you look at this additional image, you'd see here three angle of attack for this particular airfoil. So when you have a low angle of attack, you have your fluid flow over most of the surface. For the stall portion, 25 degrees, there is a lot of flow separation. So the only part of the airfoil engaged in lift generation is this part, the leading edge. Now, when it comes to the middle, uh, this is what the image claims is when the airfoil generates its maximum lift. Now, take note of this. Even though it is generating its highest amount of lift in this angle, there is still part of the upper surface that is disengaged. Essentially, part of the trailing side of the upper surface uh, no longer has any fluid flowing over it, or at least um, no flow that helps in generating lift. So even though only part of the upper surface is helping with lift, it is still generating its maximum lift. Sorry. Now that I've mentioned airfoil testing, it is important indeed to know where the stall angle is. Hence why we usually see a lot of performance testing involved for airfoils. And we usually do that through wind tunnels. So a wind tunnel has a lot of static and dynamic parts. Its very root is just to generate a laminar and a uniform velocity at the test section. So all of these parts are just to produce a laminar and a uniform velocity distribution at this section. And here, usually you put something that you want to test out. If you look at this image at the right of the wind tunnel, this is an example of a testing rig. So you can place this testing rig here in the open section. And once the fluid flows over the airfoil, there will be a particular pressure, particular forces that are being felt by that airfoil, and that can be recorded during the test. Now, there are two ways to measure the lift, drag, and other forces, other relevant criteria on an airfoil. The first one is usually the one most research centers go for, and that is the wall-mounted pressure tap airfoil. So there are two configurations. You can have it wall-mounted like this. So essentially, your test section is closed off, or you can have something like this. You have a rig. You can place this in an open test section of a wind tunnel, and it will basically record data um, as the fluid flows. There might be some differences in what this records, but we will not discuss those differences now. So what you'd have here in this particular setup is that you'll have these little holes along the midpoint circumference of your airfoil. Now, for some pressure tap airfoils, you might be interested in holes here aside from the midpoint. But basically, the point of these taps is that you can connect some pressure tubing to those taps, and then you can record basically the pressure on that point of the airfoil. Now, the neat thing about this is that with this, you can actually develop an experimental pressure distribution along your airfoil. And this is, in fact, how a lot of the old airfoil data has been calculated. So you typically see tables upon tables of pressure distribution data. Sometimes they don't generate the lift and drag tables anymore. They just go right ahead and maintain the pressure distribution. And it is true that from there you can generate those data, the lift, drag, whatever it is that you want to generate. The difficulty with this setup though is that those taps, the insertion of the pressure tubing also can be a bit complex and expensive. So even though there is a mountain of data that you can look at through the pressure distribution alone, you might not have the capacity to actually manufacture this kind of pressure tap airfoil. And if you don't have that capacity, you can go for the next best thing, which is this what we call the sting setup. So the sting is kind of like a cantilever mount where you just place your object for testing. So this can be an airfoil, this can be an aircraft body, this can be a ball or something else. This kind of setup directly measures the lift, drag, and other forces that you want to measure from the wind tunnel setup. You won't get any pressure distribution recordings here, just the lift, drag, moment, etc. Now, this might not have as great of a data as you expected, but it is kind of still useful, especially if you're just after the lift and drag. Basically, sometimes pressure tapping is too complex you need a lot of taps. Sometimes, if you try to tap a complex object, you might need a very expensive setup. So for sting fixtures, this is the more accessible. And sometimes it's good enough for that. All right. So now let's talk about airfoil families. Our focus for this experiment would be one particular family, which is the one generated by the National Advisory Committee on Aeronautics, or its successor, NASA. So NACA or NASA then, well, NASA or NACA then had this particular research center, and they've been doing a lot of these airfoil tests for 100 years now, since 100 years ago. So they had this particular naming scheme that is quite convenient because the naming scheme they chose actually displays key characteristics of the airfoil from outright. So they started at first with a four-digit family, and then they actually expanded it to seven digits. To give you an idea of the age of this family, they were able to reach six digits by around the latter half of World War II, just 1940s, 1950s. So this family is very old. But because of that particular naming scheme, uh, it is quite convenient to generate airfoils through that. And they do actually have public equations for generating the four-digit and five-digit. I think six-digit. The six-digit formula is also available. I'm not sure. You can check it out. And if you plug in that equation, you can generate the airfoil from scratch. All right. Let's go to the four-digit naming scheme in particular. When I say, for example, NACA 4412, those digits pertain to a particular geometry aspect of that airfoil. So for the last two digits, 1, 2, this pertains to the maximum thickness. So when I say NACA 4412, it says that the maximum thickness of that airfoil is 12% of the chord length. 12% of the chord length. Alright? Now the first two digits then refer to the maximum camber. So if I say NACA 0012, I'm saying that it has a camber of 0. Essentially, it is symmetric. Now I say 4412, the first digit is the actual maximum camber. So 4412 has a maximum camber of 4%. Now that 4% maximum camber is located 40% from the trailing edge. So 4412 is 4% maximum camber at 40% from the leading edge, and its maximum thickness is 12% of the chord length. It doesn't say where the chord length maximum, or rather the maximum thickness is, but it is what it is. So there are more advanced NACA terminologies, like for example, the NACA 5-digit naming scheme actually includes the design lift, or the design maximum lift of this airplane. So we will not tackle that, but you can be free to explore on how they actually decided on what the design lift is and how that influences the geometry of the airfoil. But we'll leave that for later for you to explore on your own. Now, we don't actually have a airfoil testing center here in LB. We do have a wind tunnel, but we don't have a viable testing rig for airfoils. So we'll go to the next best thing, which is simulation. Now, to preface this, I do not have any actual work experience in simulating airfoils for fluid dynamics. Rather, um, my closest experience with this is with our ME 171 equivalent in Diliman. So this was taught by one of our professors then. He is now Professor 12, which is the highest rank that a UP professor can possibly reach. So good on him. And he dumped this particular software on us, Cublade. He taught us how to use it, what those buttons meant, but he didn't teach us the theory is basically okay. So this is the software. This is how to use it. Now this here's the project. Now do this. That's what happened with us. It was basically okay. We had to pick this up on our own, but we didn't understand the theorems behind it. But for your case, I'll try my best to discuss what those theorems are. Now, a lot of the airfoil simulations, at least the light ones, the ones we'll be using for this experiment and the next one, involves the X-foil program. So the X-foil program is pretty old. It was developed in Massachusetts Institute of Technology, and it's still being used now because even though it's computationally light, it's quite simple. It does generate fairly accurate results, especially at the subsonic regime. So sometimes you don't have to go to CFD immediately because if you compare the data for CFD and Xfoil, sometimes there are flow regimes where Xfoil actually wins in accuracy over CFD, and that means a lot because CFD is very intensive on your computer. Now, how does Xfoil actually work? So Xfoil works by first breaking apart your airfoil into several flat panels. Now, at the midpoint of those panels, it will assume that there's a swirling vortex in the middle of that panel. Now, this is crazy because there is no vortex that is being generated along the airfoil at any point in real life circumstances, but that is just the initiating condition. Now, there are also boundary conditions, and we won't discuss those boundary conditions there. But basically, it's going to try to resolve the fluid flow from that initial condition. And what it will develop is a particular pressure distribution around the airfoil. Now, X-foil uses non-viscous formulas, and then it's going to punch in some correction factors later on. So I think that's one of the factors why it's quite light. So it starts with a very simple equation, and then it corrects for it in post. I am not sure if that is how it actually works, but that is my understanding of the thesis and the lectures on X-Foil. You can go verify that for yourself if you want. You can correct me also in the chat or in the comments. Now, what do you need to feed to this X-Foil program? You basically need to feed it fluid flow characteristics and some information on the airfoil. So for fluid flow characteristics, you need to feed it the density, the viscosity of the fluid, and of course the Reynolds number, the flow regime of your. So if you want to simulate your airflow at varying flow regimes or at varying altitudes in the atmosphere, you have to run a different test essentially. Now for the angle of attack, this is quite important. You have to specify the range of the angle of attack that you want to examine. So for example, I want to examine airflow from 0 to 15 degrees angle of attack. So you have to say that, and then you have to say what increments. Like, do I want my increments to be fine, like zero point 0.1 degrees, zero point 0.1, zero point 0.2, zero point 0.3, or is it okay if I just go default, like 1 degree, so 0, 1, 2, 3. Now, another thing to specify is the transition settings for laminar and turbulent flow. So this occurs over the airfoil, but you have two options in Xfoil. You can leave the program to actually guess where the transition happens, or you can just straight up say the transition will happen at this point. Now, when you say the program is free to essentially solve for the transition point, it will ask you this particular quantity, ncrit. Ncrit is, I think it's unique to Xfoil, I'm not sure, but this basically describes how unruly or how unideal or basically how rough the velocity profile of your wind is. So usually this is left at default 9 because that encrypt value is matched with a average quality wind tunnel. Now, if you look at the activity guide, there is actually the table of NCRIT values. You can check that if you want. So if you're using XFOL to simulate high altitude flight, I believe there is a particular XFOL. There's a particular NCRIT number for that. So now, if you want to force the transition, usually you do this when you're examining flaps or some addition to the airfoil that breaks up the flow. So that includes leading edge flaps or some other thing. So usually when you're forcing the transition, you're just trying to say, okay, so my flap is located here, and I want to simulate what happens when I activate this flap, right? So once you've done that, the X-foil will run its code, and usually it will start at every angle of attack to produce this pressure distribution around that airfoil. So this is usually stored in what X-foil calls the up point. So each angle of attack will have its up point data, and you have the option of saving that up point data. Now, from that up point data, it will calculate the lift coefficient, the drag coefficient, the moment coefficient, and among others. Now, what would that data look like? It kind of looks something like this. So this is the up point data in Xfloor 5. So Xfloor 5 is kind of like Q-Blade, but it is more leaning towards fixed wing aircraft design. So this is the pressure distribution along a particular airfoil at a particular angle of attack. And what you notice here is that the y-axis is actually topsy-turvy. It is upside down. So this is a pressure distribution y-axis, but the positive direction is all negative. Now you have two parts of this curve. You have the upper portion and you have the lower portion. So this indicates that the upper portion is experiencing a lot of suction, essentially. So the higher the upper surface curve is, the more suction it is experiencing at that particular area. And you can also ask Xfoil to plot that pressure distribution as is on the aircraft or the airfoil rather itself. And you can actually ask Xfoil to simulate the boundary layer over that particular airfoil. So in this case, you kind of see some flow separation, but even though there is flow separation, it is generating quite a lot of lift. Now, from that up point data, that pressure distribution data, it will generate these curves. So you have your lift versus angle of attack, you have your drag versus angle of attack, you have your lift over drag ratio versus angle of attack, and you have this particular thing. This is called the moment coefficient. This quantifies the amount of twisting that your airfoil will feel as the flow is moving over your aircraft. So if you're just testing for an airfoil, uh, you can kind of record this. However, the moment coefficient is more relevant when you have three-dimensional structures. It quantifies the amount of twisting that structure, that airfoil will feel in that particular condition. And that's basically it. We are done with airfoil performance simulation. However, before we proceed with the experiment, I plan on opening with a slight test, or rather a slight demo and a guided tour to the program. We are actually using two different programs for experiment 4 and 5. We're going to use Explore 5 for experiment 4 and then QBlade for experiment 5. My reasoning for that is that you can have more exposure to these different kinds of programs. These are open source. You can freely download them with no piracy concerns. And I think it just lets you take in just how wide and how full of breadth our degree program is. Like there's a lot going on in each of those niches that we don't get to explore that much in our curriculum. And I hope that through exposure to different kinds of programs, you can kind of glean into what direction you want to do for your thesis or what direction you want to take after you graduate from this university. So, guys, so thank you so much.